Hello everyone, welcome to CLA. So in this video, we will be going over the concepts of set theory, and then in the next part of this topic, we will be discussing the questions as well. So without any further delay, let's start with the module. So first of all, we need to look at what is a set. Okay. So yes, so let's begin with the concept first. The set is actually a well-defined collection of distinct objects. So, for simply explaining this, let's say I take the letters of the word school. Okay. Now, if I want to represent it in the form of sets, then I need to put curly braces. This is one of the representation which is known as the roster form. In the roster form, when you represent the elements, they have to be distinct, and the order also doesn't matter. So, for example, the letters of the word school can be represented in this manner. I could have written the C, H, and O anywhere I would have wanted. So, this is how we represent the set in a roster format. Similarly, you can represent numbers, characters, anything in a set. Okay. Let's move on to the next area where we know about the ways in which we represent the set. So, as you can see, that we have mainly two ways in which we can represent the set, and the first way is the roster form, which I have already discussed in the previous slide, that we put some curly braces and then list all the elements in a comma separated manner. The next format is the set builder format. Here actually we define a particular rule which the element of the set will follow. So the element of the set is actually represented by this variable x, and then we define some rules which we write on the right hand side of this colon symbol. This colon symbol represents such that. Okay. So when you read this set builder notation, the reading should be like the set of all x such that x is a positive integer less than 6. What does this mean actually? So if I have to represent this in the roster form, then I'll put the curly braces and positive integer less than 6. So positive integer will begin from 1 and it will continue up to 5. It will not include 6 because I have mentioned less than 6. Okay. And there's another important point. It's not a representation, and it is basically the representation of a null set or an empty set. This we also call it as null set. So we can either represent it by empty curly braces, or we can use this phi symbol for denoting the null set. Okay. Now next we move on to a very important concept, which is of the subset. So here the example is very intuitive. Say this larger circle is the set of all fruits, and the smaller blue circle is the set of all apples. So clearly you can see that the apple is a subset of the fruits. So all the apples will come within the larger parent collection of fruits. Okay, so that is known as the subset. Let's move on to the notation. So this notation is actually very important. When we say that a particular set is a subset of another set, we denote it using this symbol. A is a subset of B, and here this actually means that this element A, small a belongs to A, and small a also belongs to B. So basically, if A is a subset of B, then every element which is belonging to this A subset will by default also be an element of the B set. Okay. Now, when we extend this idea in the reverse manner, so if A is a subset of B and also B is a subset of A, then in that case, we actually are saying that A and B are equal. Okay. So think logically that in both ways we define the grouping. So we are saying that A is contained within B, and we are also saying that B is contained within A. This can happen if and only if both the sets are equal. So we don't have any like different circle in representing it. So A and B are overlapping. That's why we have A equal to B when two sets are exactly the same. Next, we move on to the very important concept of power set. So the subset is defined like this. So we have a set A, which is like kind of a subset of B. Then the total number of subsets possible from a given set which has n elements, that is actually given by this formula. This is 2 to the power n. So for example, I have a set which is having 2 elements, okay, 1 and 2. This is one particular set. Now, what will be the total number of subsets of this uh, set A? So we denote this using the power set. The collection of, it will be the set of subsets of a particular element. So first I can take one element. So 1 and 2, these will be the subset. Next I can take both elements. So this is basically the entire set A. And also there will be a fourth element, which is the null set. So you have to remember that every subset will contain the original set itself as well as the null set. So that's why we say that the number of elements the number of subsets possible from a given set A is 2 to the power n. In this case, n is 2, so 2 to the power 2, which will be 4. That is exactly the number of elements represented in this power set. So power set is simply the set of all the subsets, and therefore the number of elements in the power set will always be equal to the total number of subsets possible from the given set having n elements. Okay, I hope this part is clear, and this is actually very helpful. Okay, now next we move on to another interesting concept of Venn diagrams. So in this particular slide, you can see that I have represented apples as an inner circle and fruits as an outer circle. So this is basically the concept of, this is a crude example of Venn diagrams only. Let's move on to a practical example. So we all know that there are different types of numbers, right? We are familiar with different types of numbers. For example, in this particular diagram, W is basically denoting whole numbers, N is denoting natural numbers, and Z is denoting integers. The U, which is written over here, this is known as the universal set. The meaning of the universal set is, so this W, N and Z, all of these are subsets of this universal set. So this is kind of a parent set. So you can consider the universal set as of now, let's consider it to be real numbers. We are not going to the complex domain as of now. So let's consider the universal set as real numbers. So within that, there will be the set of integers. This will have both positive and negative both positive and negative numbers. For example, -2 can be there, +5 can be there, -100 can be there, +1000 can be there. So these kind of numbers are known as integers. Also, there will be natural numbers. So what are natural numbers? Natural numbers are basically positive integers greater than or equal to 1. Right? Positive integers which are greater than or equal to 1, these are known as natural numbers. This whole number is actually again a subset of the natural number. It was not represented here. So what is the difference? Okay, sorry, I made a mistake here. So this natural number is actually a subset of the whole number. The reason is that 0 is also considered as part of this whole number. But in natural numbers, we don't have 0. We have starting from 1 till all the positive integers, right? So this is how we represent the Venn diagram, where each of the circle represents a particular subset and their relationship among them, right? As you can see, given circles represent the individual subsets and overlapping areas represent the shared elements. So yes, that is fine. And yeah, now we move on to another important term, that is the union and the intersection. So when we say that we need to take union of two sets. That is basically an inclusive OR. Or if you are from electronics background, we can say that this is the OR operator or the plus symbol. And the intersection is basically the common part from both of the entities. So, for example, if this is set A and this is set B, then this common part is known as the intersection, and this is denoted by A intersection of B. Similarly, if we have two sets, set A and set B, and if we have to take the union of set A and set B, that will be a collection of all the members. In this case, it is represented as a disjoint subset. What do we mean by disjoint? So, when A intersection B is a null set, when we don't have any common elements between the two sets, we can denote them as disjoint sets. Okay? Yeah. So, exactly the concept which I discussed just now, that we have disjoint sets here when A intersection B is a null set. And similarly, when we have two sets and we need to take the union, we consider all of this part. So this A union B represents all of the blue shaded portion. Similarly, for intersection, we have this common part, the blue shaded portion, which denotes the intersection or the common elements, the overlapping part of both A and B. Okay. Right. Now, there is another important notation. Before moving on to difference, I'll like to spend some time on the complement part. So, we have this universal set, okay? Universal set is U, and we have a set which is A, okay? Now, when we say that I have to take the complement of A basically means that I want everything which is outside of A, okay? So, this entire part, which is not considering the A, but everything else in the universal set, in this case, this is known as the complement. And similarly, the complement is such an operator, if you apply it once again, you get the setback. So, I mean, setback in the sense, when you take the complement of complement, it basically cancels out and you get the original set. So, this is basically our complement operator here. So, you can consider this similar to the NOT gate or the NOT operator. Okay. Now, one important concept which people face some difficulty in understanding is the difference between sets. Okay. Okay, my pen is not working properly. Yeah. So, let's say we have a set A and we have a set B. I'm representing a Venn diagram formation. Okay. Now, if I want this result A minus B, what does it mean? So, the meaning of this expression is that I want all the elements of set A only. I don't want set B at all. So, this overlap portion which is there with set A, this is the intersection, right? I have told you this is the A intersection B, and this is the entire set B. So, this set B contains this shaded part plus the intersection part. So, I want this entire thing to be subtracted from the set A. Okay, right? So, that is the physical meaning of the difference A minus B. Okay. So, yeah, that's what I just now explained, that the difference A minus B is basically a set where the elements will belong to A, but they will not belong to B. Okay, that's the meaning of A minus B. And complement also I have discussed that the element should belong to the universal set and it should not belong to A. So, basically the shaded part here, okay, this set A we are not touching. We are considering only the shaded part as part of the universal set. Now, in related to this, we have some important laws which are known as De Morgan's laws, and these are widely used in the semiconductor domain as well, right? So, we have De Morgan's laws here, where we take the complement of union and we get individual complements with an intersection sign. Similarly, for A intersection B, if we take a complement, we get individual complements and we take the union. Okay. These are very simple to apply, and these are mainly used for simplifying some Boolean expression, or later you will see when we have some mixed expressions involving unions and intersections. These laws are actually very helpful. Right. So these cardinality formulas, these are, okay, I'll explain it later. Yeah. So mainly we have two formulas here. So the first formula is actually based on two sets, and the next formula, this is 1, this is 2. First formula is based on 2 sets, and the next formula is based on 3 sets. Okay. Now, if I just tell you that this is a formula, then it will be very difficult. So let me illustrate this using a diagram. Let us go here. Let's understand the first formula. Okay. Let's say we have 2 sets. Okay. We have set A, we have set B, and we have the intersection part. Okay. This part where, okay, let me change the color of the pen first. Yeah. So this part here, which is denoted by 2, this is actually my A intersection B. Okay. Can you tell me that how can we represent this part 3 over here? Only this part 3. I don't want 2, I don't want 1. Right? So this is actually denoted by B minus A, difference of A from B. Okay. And similarly, this one part is represented as A minus B. So we have got 1, we have got 3, and we have got 2. So basically we can say that A union B is actually the, okay, let's consider numbers here. The number of elements in A union B is actually the addition of A minus B, B minus A, and A intersection B. You might find this as a formula somewhere, but I have just explained you visually that what it exactly means, right? Okay, now coming on to our original formula. If you want to find the union of A and B, then what you can see is that the first term of the formula says we have to take the number of elements of A. Okay, so number of elements of A will be 1 and 2 from this diagram. Similarly, we have to take number of elements of B. B will be 2 and 3. Okay, I should write here 1 plus 2. Let's consider this now. Okay, let's remove it entirely. Right. So 1 plus 2 is my NA. Then NB is 2 plus 3, because 2 also belongs to B and 3 also belongs to B. So if we add NA and NB, we are finding that we have 1 plus 3 plus we have 2 times 2, right? So this duplicate 2 has come because we have added this intersection part twice. Therefore, we need to subtract the intersection once, and that is the reason why this formula has come into existence, where if you want to find the union of 2 sets, then we add the individual elements and then subtract the intersection from them. And this is actually a very useful formula, the 3-set formula, where we add up all the 3 elements and then we try to adjust it using these differences. We subtract the 2-set intersections, and at the end we add the 3-set intersection, right? So let's see how this formula has evolved. Yeah, this is a cleaner diagram. Okay, so when we consider set A, we have 1 plus 4 plus 2 plus 3, right? This is my set A. Then I have set B, which is 4 plus 5 plus 3 plus 6. This is my set B. Similarly, set C will be 2 plus 3 plus 6 plus 7. Okay. Now, I can think of adding all of these up. So if I add this, then all of these elements will be added. Okay. Now let me write down these parts as well, the intersection parts. So if I try to subtract A intersection B, that is which portion? This is 4 and 3, right? So 4 and 3 is the A intersection B part. So minus 4 minus 3. Similarly, for B intersection C, I have 3 and 6. Similarly, for A intersection C, I have 2 and 3, right? So now if you try to add all of these up, then you'll find that we have 1 plus, okay, 4 is getting twice and then we subtract it. So 2 times we have 4, right? I'm doing something wrong here. Okay, this is fine. Our motive is to get right. So we have 1. So ultimately, we will be getting, as the result, we'll be getting 1. And then 4, we are adding ones and we are nullifying this 4 and this 4. So 4 we have ones, then 2, we have 2 here, we have 2 here and we are nullifying the 2 here. So we have 2 ones and 3. 3 we are having 1 3 here, 2 3s here and we are nullifying both the 3s here, right? So we are having plus 3 also, right? We are having 5 one time only. We are having 7 I can see one time. So 1 5 7 we have. We are having 4 2 3 as well. And we are having 6 also getting nullified. So 6 also we are having, right? And I think 2 something we are having twice actually. So 1 4 2 3 is my set A. Then set B is 4 5 3 6, that is fine. 2 3 6 7 is my set C. And 4 3 I am subtracting A intersection B, B intersection C, A intersection C. Okay, we have 3 here 2 times. Okay, we have 3 actually 3 times, right? We have 3 times and we are subtracting 3 also 3 times. So basically we don't have 3 in the result. Sorry, that was my mistake. We don't have 3 in the result, but we actually want the 3 to be in the result. So for this reason, we add this intersection of 3 sets. So as you can see, the intersection of 3 sets basically represents the number 3 here. Okay. So from this simple like workout, you can see that like how this particular 3 set formula has come into existence. So before memorizing, you can always try with a pen and paper that how this formula is actually behaving. So that was it all about the concept regarding the sets. In the next session, we'll be looking at some of the NCERT exemplar problems related to this particular concepts. So thank you all for joining. Let's keep learning and keep growing. See you in the next video.